The following video goes over solving exponential and logarithmic equations. Since we did this last year, I'm going to try and review this in a relatively quick format. If I have exponential functions such that I have powers that have the same type of base, 2 to the x plus 1 equals 4, I can rewrite the 4 in terms of 2's, and then I can just set the exponents equal to each other. Likewise, 3 to the 2n plus 1, or 2n minus 1, sorry, equals 81. I can rewrite 81 as 3 to the 4th. Then I can set the exponents equal to each other. So n equals 5 halves. I can do the same thing in slightly more complicated problems. So I have 3 to the x squared equals 3 squared to the x. Then I can remember my exponent rules. And power to a power means I multiply the exponents. So x squared has to equal 2x. And then I solve this by factoring. And I end up with x equals 0 and x equals 2. Number 3 and number 4, I have 2 to the x times 2 to the negative 3x equals 2 to the 2x. Then when I multiply these, I add the exponents. So 2 to the negative 2x equals 2 to the 2x. So I set the exponents equal, and the only way that's going to happen is if x equals 0. Over here I have e to the x squared equals e to the 3x times 1 over 3 to the 2, which is the same thing as e to the 3x divided by e squared. And using the exponent rules, that's e to the 3x minus 2. So I can set these two exponents equal to each other. Then I'll factor x minus 2, x minus 1. So x equals 2 and x equals 1. Number 5 is a little bit more challenging. If 7 to the negative x equals 1/3, what is 7 to the 5x? So what I can probably do is just realize that 7 to the x equals 3, because the negative exponent means it's a reciprocal. So 7 to the x would equal 3. So then I have 7 to the 5x. Well, what is 7 to the 5x going to be equal to? Well, that would be equal to 3 to the 5th, because I just take both sides of this equation to the 5th power. So 3 to the 5th, I'll just count by 3's. 3, 9, 27, 81, 243. So the answer is 243. Now log equations work much in the same way as exponential equations. If I have logs with the same base, then the insides have to be equal to each other. So 3x equals 5x minus 8. The only difference is, in exponential functions, I do not have any domain restrictions. So 1, 5 halves, 0, 2, I never really had to check anything. As long as I did the algebra right, I'm fine. But in this problem, when I solve for x, I should probably make sure that I don't get any domain restriction problems, because the inside of a log has to be greater than 0. It cannot be even equal to 0. So if I substitute 4 back in, both sides of the equation have the inside greater than 0, so that ends up working out. But that's something that I have to continually check. And that's especially true once I start having to factor things. So, problem 7, all of these are log base 3's. When I have This plus in the middle, I'm going to use one of the rules of logs, where when I add two different logs, that's the same thing as multiplying the interiors and keeping a log base 3 here. So I'm going to set these two things equal. So x cubed minus 8x, the inside of the left side, is going to equal the inside of the right side. So I end up with x to the cubed, not x to the cubed, x to the third, or x cubed minus 16x equals 0. Then there's some factoring that occurs. So x equals 0, 4, and negative 4. And we just have to make sure that in all cases I end up with insides that are bigger than 0. And when I look at this, 0 does not work because that one would not be bigger than 0. 4 seems to work, but negative 4 doesn't work. So I actually end up with only one of my three answers working. X equals 4. Natural log of square root of x plus 2 equals 1. What I would do in this case is take e to both sides. So the square root of x plus 2 equals e to the 1, which is e. Then I'm going to square both sides. Then I'm going to subtract 2. So e squared minus 2 is definitely bigger than 0, and it's definitely bigger than negative 2, so that means it's okay to be inside of the radical. So x equals e squared minus 2. One more thing that I should probably talk about is, let's say I have 3 to the x equals 7 to the 2x minus 1 or something like that. So if I have a problem that looks like this where the bases are not the same and I can't manipulate it like I did in problems 1, 2, 3, and 4, I'd have to take a log of both sides. So let's take a log base 3, for example. So log base 3 of 3 to the x just gives me x, and then I have log base 3, 7 to the 2x minus 1. Notice that then I can take this power and move it to the front by one of the log rules. And then I could distribute. This problem's going to end up taking a while. I picked some nasty numbers. Then I can subtract and there's a lot of different ways that I could have solved this problem. Then I can factor out the x. Then I can divide. I could have also solved this by taking a log base 7 of both sides. I could have taken a natural log of both sides. There's a lot of different ways to equivalently solve this. I can also give you a quicker and not as difficult one. But let's say I have 3 to the 2x plus 7 equals 11. I would just take a log base 3 of both sides. And then just solve for x here. So x equals log base 3 of 11 minus 7 over 2. So notice that this one's going to be easier because I don't have exponents on both sides. But these are ways that you can solve exponential problems that don't have common bases. Problem 9. What I could do here is I could just multiply this 1/2 over to the other side. So then I have log base 3 of x equals 4, log base 3 of 2. And I cannot equate the insides yet because one of them is a 4. But what I can do is, since I have this 4 coefficient, I can use the log rules and rewrite this 4 as an exponent. So log base 3 of 2 to the 4th is really log base 3 of 16. Then I have x equals 16. Number 10, log base 3 of 27 equals log base 4 of x squared minus 1. Well, that looks intimidating until you realize that log base 3 of 27 is actually just a nice number, right? Log base 3 of 27 is 3. Then I can rewrite this in exponential form. So 4 to the 3rd equals x squared minus 1. And 4 to the 3rd is 64. So I add 1 and take the square root. X equals plus or minus the square root of 65. And in either case, both work, because even if I plug in negative square root of 65, I don't get a negative number on the inside because it gets squared. Number 11, I'm going to rewrite this 2 as an exponent. So the square root of x squared gives me x. Then I'll use the condensing rules for logs to do x divided by 6x minus 1 on the inside of the log. So then x divided by 6x minus 1 equals 0. And the only way that that works is if x equals 0. However, x cannot be 0, because that would make the inside of a log equal to 0 in the original problem, and it would make this one equal to negative 1, which doesn't make any sense. So this has no solution. Number 13, log base 4 of x squared minus 9 minus log base 4 of x plus 3. I'm just going to use the condensing formula. And then, since x squared minus 9 factors to x plus 3x minus 3, the x plus 3's will cancel. Then I have x minus 3 equals 4 to the 3rd. 4 to the 3rd is 64. So x equals 67. The last 3 problems are really just factoring problems. So if I make a equal 3 to the x here, I have a squared minus a minus 72. You don't have to do this substitution, but sometimes it's easier for people to see when we do that. So I have a minus 9 times a plus 8. So a equals 9 and a equals negative 8. Then I can replace and put 3 to the x equals 9 and 3 to the x equals negative 8. This one will never work. On the other side, I get x equals 2. I can't have a positive to an exponent equal a negative number. Number 15, 4 to the x plus 1/2 power. Now if I think about what that means, 4 to the x plus 1/2 power is the same thing as 4 to the x times 4 to the 1/2, because I end up with, when I add the exponents, that's the same thing as multiplying two things with the same base. 4 to the 1/2 is really just 2. So this is like 2 times 4 to the x minus 2 to the x equals 28. And 4 to the x is really 2 to the 2x. So now it ends up looking a lot like this problem, number 14. So I have 2a squared minus a, and then subtract 28 from both sides, set it equal to 0. Then I factor. So I have 2a minus 4, and plus 7 is my number. So 2a plus 7 and a minus 4 should make this work. So a equals 4, which means 2 to the x equals 4. And a equals negative 7 halves, which means 2 to the x equals negative 7 halves. So x equals 2, and this one doesn't work. Now, why did I do a second problem that's similar? Because it would end up being this exact same situation. So I have 2a squared plus a minus 28. So when I factor it, I end up with 2a minus 7 and a plus 4. So I end up with a equals 7 halves and a equals negative 4. Now, a equals negative 4 is not going to work because 2 to the x can't equal negative 4. But if 2 to the x equals 7 halves, then x is going to have to equal, well, it's not going to be a nice number. It's going to be log base 2 of 7 halves. So it's important to understand that we can have kind of nasty log answers too. Then finally, number 16, 5 to the 2x. If I make a equal 5 to the x, I get a squared minus 5 to the x plus 1 is the same thing as 5 to the x times 5. So 5 times a is what I get. So when I factor this, I get a minus 3 and a minus 2. So a, which is 5 to the x, equals 3, and 5 to the x equals 2. So x equals log base 5 of 3, and x equals log base 5 of 2.